To understand why a to the power of 0 equals 1, we need to first examine the pattern that emerges when we work with decreasing exponents. Let's start with a cubed. When we write a to the power of 3, we're multiplying a by itself 3 times. This gives us a times a times a. Now what happens when we decrease the exponent by 1? Let's see how the expression changes. When the exponent decreases from 3 to 2, we get a squared, which equals a multiplied by itself twice. We have a times a. Notice what happened here. When we decrease the exponent from 3 to 2, we removed one factor of a from the expression. This is an important pattern to observe. Each time the exponent decreases by 1, we lose one factor of a in the multiplication. Let's continue with this pattern. What happens when we decrease the exponent from 2 to 1? With a to the power of 1, we're left with just a single factor of a. This is why a to the first power is simply written as a. Once again, observe what happened. When we moved from a squared to a carry to the first power, we lost another factor of a. Our pattern is holding consistent. Each time the exponent decreases by 1, one factor of a is removed from the product. Now comes the interesting part. If we follow this pattern logically, what would happen when we decrease the exponent one more time from 1 to 0? This leads us to a to the power of 0. But what value should this equal? If we're continuing our established pattern, we need to figure out what happens when we remove the last factor of a. Looking at a to the first power, we have just a single a. If we were to remove this last factor of a, what would remain? When you remove all factors from a multiplication, you're left with the multiplicative identity, which is 1. This is why a to the power of 0 equals 1. It's what remains when all factors of a have been removed. Understanding why a to the power of 0 equals 1 is a fundamental concept in algebra. It's not just a rule to memorize, but a natural consequence of the pattern of exponents and how multiplication works. This pattern-based reasoning helps us make sense of mathematical rules rather than just accepting them without understanding. This pattern-based approach to understanding zero exponents gives us insight into the structure of mathematics and helps build a stronger foundation for more complex concepts. The division property of exponents is a powerful tool that not only helps us simplify expressions, but also reveals why any non-zero number raised to the power of 0 equals 1. This formula tells us that when we divide two powers with the same base a, we keep the base and subtract the exponents. For example, a to the power of m divided by a to the power of n equals a to the power of m minus n. To understand why a to the power of 0 equals 1, let's examine what happens when we divide a power by itself. Here we have a to the power of 5 divided by a to the power of 5. Intuitively, we know that dividing any non-zero number by itself gives us 1, so this expression must equal 1. But let's apply our division property. According to our formula, we subtract the exponents, 5 minus 5, which gives us 0. So a to the power of 5 divided by a to the power of 5 equals a to the power of 0. To see why this makes sense, let's write out what a to the power of 5 actually means. In the numerator, we have a multiplied by itself 5 times, and in the denominator, we also have a multiplied by itself 5 times. When we simplify a fraction, we can cancel out common factors in the numerator and denominator. Let's cancel each factor of a from the top with its corresponding factor at the bottom. After all 5 factors of a cancel out from both the top and bottom, what remains is simply 1. This is because any number divided by itself equals 1 as long as the number isn't 0. So we've shown that a to the power of 5 divided by a to the power of 5 equals 1. But we also know from our division property that this same expression equals a to the power of 0. Since both expressions equal the same thing, we can conclude that a to the power of 0 must equal 1. This is true for any non-zero base. This is a fundamental rule in algebra. Any non-zero number raised to the power of 0 equals 1. Whether it's 2 to the power of 0, 10 to the power of 0, or even complicated expressions like the quantity x squared plus y squared to the power of 0, they all equal 1. Understanding this zero exponent rule is essential for algebra, as it appears frequently in simplifying expressions and solving equations with variables raised to different powers. To summarize what we've learned, the division property of exponents tells us that when dividing powers with the same base, we subtract the exponents. When those exponents are equal, like in a to the power of 5 divided by a to the power of 5, we get a to the power of 0. And through our cancellation demonstration, we've proven that a to the power of 0 equals 1. Scientific notation is a powerful way to express very large and very small numbers in a concise format. Today, we'll explore how the zero exponent rule plays a crucial role in this system. In scientific notation, we express numbers as a coefficient a multiplied by 10 raised to a power b. The coefficient a is always greater than or equal to 1, but less than 10. This gives us a standardized way to write all numbers. Let's see how this works with some examples. The number 5,200 can be written as 5.2 times 10 to the power of 3. To convert to scientific notation, we move the decimal point 3 places to the left to get 5.2, and then multiplied by 10 cubed to maintain the original value. For the number 52, we move the decimal point 1 place to the left to get 5.2, and then multiply by 10 to the power of 1, or simply 10. This follows the same pattern. The exponent tells us how many places to shift the decimal point. Now, what about the number 5.2 itself? The decimal is already in the right position, but to maintain consistency in our notation system, we write it as 5.2 times 10 to the power of 0. This is where understanding the zero exponent becomes crucial. Let's look more closely at 5.2 times 10 to the power of 0. What does this mean mathematically, and why does it equal 5.2? The key insight here is the zero exponent rule from algebra. Any non-zero number raised to the power of 0 equals 1. This fundamental rule applies to all non-zero numbers, including 10. So 10 to the power of 0 equals 1. This means our expression simplifies to 5.2 times 1. And since any number multiplied by 1 equals itself, 5.2 times 1 equals 5.2. This confirms that our scientific notation expression gives us the correct value. This simple property, that a raised to the power of 0 equals 1 for any non-zero a, creates a beautiful consistency in our number system. Without it, scientific notation would require special cases for numbers between 1 and 10. This pattern works identically for all numbers. Take 7.8, for example. We can write it as 7.8 times 10 to the power of 0, which equals 7.8, since 10 to the power of 0 equals 1. The zero exponent provides a seamless way to represent any number in scientific notation. The zero exponent rule allows scientific notation to work as a unified system. Without it, we'd need a special case for numbers between 1 and 10, breaking the elegant pattern we see across the number line. The key takeaway is that any non-zero number raised to the power of 0 equals 1. This seemingly simple rule is what allows our number system to maintain consistency and elegance, particularly when working with scientific notation. Let's examine why a raised to the power of 0 equals 1. A rule that might seem arbitrary at first, but is actually a mathematical necessity. Our first piece of evidence comes from pattern consistency in exponent sequences. When we look at descending powers, we can identify a clear pattern. Looking at this sequence, we can see that a cubed equals a squared times a. As we continue down, a squared equals to the first power times a, and a to the first power equals a to the 0 power times a. For this pattern to remain consistent, when we reach a to the 0 power, it must equal 1. If we used any other value, the pattern would break down, and mathematics thrives on consistent patterns. Our second piece of evidence comes from the division property of exponents, one of the fundamental rules of algebra. The division property tells us that when we divide a to the power of m by a to the power of n, we get a to the power of m minus n. This is a core rule in exponent operations. Let's apply this rule with a specific example. If we divide a to the power of 5 by a to the power of 5, according to our rule, we get a to the power of 5 minus 5, which is a to the power of 0. But we also know from basic arithmetic that any non-zero number divided by itself always equals 1. This is true regardless of what value it represents. This gives us a direct logical proof. If a to the power of 0 equals both 1 and the result of a to the power of 5 minus 5, then a to the power of 0 must equal 1. Our third piece of evidence relates to the elegance and internal consistency of mathematics as a unified system. Mathematics works as an interconnected system where all rules must function harmoniously together. If a to the power of 0 were anything other than 1, the entire structure of exponent laws would collapse. These properties, the multiplication rule, the division rule, and the power-to-power rule, all interconnect perfectly when a to the power of 0 equals 1. If we assigned any other value to a to the power of 0, we'd create contradictions throughout algebra. Together, these three perspectives, pattern consistency, the division property, and mathematical elegance, form a compelling case that defining it to the power of 0 as 1 isn't just convenient, but mathematically necessary. The definition a to the power of 0 equals 1 isn't an arbitrary choice mathematicians made. It's a logical necessity that enables consistent arithmetic and algebraic operations. Understanding why to the power of 0 equals 1 helps us appreciate that mathematics isn't built on arbitrary rules, but on logical necessities that create a beautiful, interconnected system.